Hello again. Today we've moved on to the 10th of our 11th problem sets. And so this one covers chapter 29. And so we have 6 problems for the recitation and then 4 for the homework that's due next Monday. So the first problem, a circular wire loop of radius r equals 12 centimeters is immersed in a uniform magnetic field B is equal to 0.500 Tesla, with its plane normal to the direction of the field. As the field magnitude then decreases at a constant rate of negative 0.10 Tesla per second, at what rate should R increase so that the induced EMF within the loop is 0? So the induced EMF is proportional to the rate of change of the magnetic flux. So what you're going to do, or to the derivative with respect to time of the magnetic flux. So what you're going to do is determine algebraically the magnetic flux, take the derivative with respect to time, set it equal to 0, and figure out what dr over dt is. So that's problem number 5. For problem number 7, a 16 centimeter diameter circular loop of wire is placed in a 0.50 Tesla magnetic field. When the plane of the loop is perpendicular to the field lines, what is the magnetic flux through the loop? The plane of the loop is rotated so that until it makes an angle of 35 degrees with the field lines. What is the angle theta in equation 29(1a) for this situation? So remember, theta is the angle that the magnetic field makes with a line that's perpendicular to the plane of the loop. And so what is the magnetic flux through the loop at this angle? So once you figure out theta, that's pretty straightforward. Then we move on to number 8. If the resistance of the resistor in figure 2938 is slowly increased, what is the direction induced in the small circular loop inside the larger loop? So you basically have 2 loops, an outer loop and an inner loop, and one is connected to a resistor with a power supply, so it has a current running through it. And so if you increase the resistor, what is happening to the current, and then what is happening that's going through that particular loop, and then what is happening to the magnetic field generated by that loop, and how is that affecting the magnetic flux in the small circular loop? And then what would it be if the small loop were placed outside the larger one to the left? So the key to solving both of these is to figure out what is the direction of the magnetic field, or at least the primary direction of the magnetic field through the loop in each case. And you figure out the direction, and then you apply Lenz's law. Again, the induced current will oppose the change in the magnetic flux. So if the resistance is increasing, that means the current and the magnetic field are decreasing. So the induced current is going to create a magnetic field that goes which way. And so you have enough information to figure that out. And then we move on to number 32. When a car drives through the Earth's magnetic field, an EMF is induced in its vertical 75.0 centimeter long radio antenna. So it's vertical. It's in the z direction. And if the Earth's field, 5.0 times 10 to the negative 5 Tesla, points north with a dip angle of 45 degrees, so the Earth's magnetic field has a north component or a J component, and it also has a downward component, so in the negative K direction. What is the maximum EMF induced in the antenna? So use the general equation. So that's V cross B dot dl. You don't have to do any integration here, but figure out algebraically, and in which direction will the car be moving to produce this maximum value. So it's V cross B dot dl. And so basically dl is just the length of the antenna, which is in the z direction. And so you figure that out, and the car speed is 30.0 meters per second on a horizontal road. So it could have X components, it could have Y components. And you're asked to figure out how the EMF is maximized and which direction the car would need to go for the EMF to be maximized. So that brings us to number 38. A simple generator has a 480 loop square coil, 22.0 centimeters on a side. How fast must it turn in a 0.550 Tesla field? So it's rotating in a magnetic field to produce 120 volt peak output. So again, the maximum induced voltage is NBA omega. You're given N, you're given B, you're given enough information to figure out A, and you're asked to solve for omega, basically. How fast must it turn? And that brings us to 48, the last of our recitation problems. The model train transformer plugs into 120 volt AC and draws 0.35 amps while supplying 7.5 amps to the train. So the input current is 0.35 amps. The output current is 7.5 amps. So what voltage is present across the tracks? So it's got 120 volts and 0.35 amps coming in. What is the output voltage, and is the transformer step up or step down? So remember, when the voltage goes up, the current goes down, and vice versa, but the product of voltage and current remains constant. So now we'll move on to the homework problems. We'll start with number 9, and this is a solenoid. If the solenoid is being pulled away from the loop shown, so that's if, not is. So if the solenoid is being pulled away from the loop shown, in what direction is the induced current in the loop? So again, you're applying Lenz's law. Number 18, the magnetic flux through each loop of a 75 loop coil is given as a function of time, where the time t is given in seconds. Determine the EMF as a function of time. So again, apply Faraday's law of induction, and then figure out a specific value at t is equal to 1.0 seconds and t is equal to 4.0 seconds. For problem 40, a 250 loop circular armature coil with a diameter of 10.0 meters rotates at 120 revolutions per second. Remember, omega, in order for the math to work out properly, needs to be in radians per second. So you're going to need to do a little bit of a conversion in a uniform magnetic field of strength 0.45 Tesla. What is the RMS voltage output of the generator? So you figure out the maximum voltage and you divide the maximum voltage by the square root of 2 to get the RMS voltage. What would you do to the rotation frequency in order to double the RMS voltage output? And that's pretty straightforward. I mean, if you've solved the first part, solving the second part should be fairly simple. And that brings us to the last problem, which is number 50. If 65 megawatts of power at 45 kilovolts RMS arrives at a town from a generator via 3.0 ohm transmission lines, calculate the EMF at the generator end of the lines. So you've got a certain amount of voltage, but there's going to be a voltage lost within the line. And you can figure that out from the information you have. So you have the power and you have the RMS voltage. So you can figure out the RMS current from that. And you can figure out the power lost from that. And you can also figure out the voltage lost from that as well. And so there are a couple of ways you can do that. So you have the RMS current and you have the resistance, and that should give you the RMS voltage that's lost And so you have the EMF at the generator end of the lines, and you can express that as an RMS voltage if you like. And the function or the fraction of the power generated that is wasted in the lines. So how much power, so 65 megawatts of power arrives. What was the initial output power, and how much power as a percentage of the initial output power is lost? So there are a couple of steps to doing the calculation. So basically, in the course of part A, you can figure out the power at the generator end of the lines as well. And so that'll make solving part B simpler. Okay, so you have any questions, just email me. Please get the recitation demonstrations in by Friday. I'll have your group set up either tonight or tomorrow. And again, if you have any questions, don't hesitate to ask me via email. If you want to talk to me directly, you can always, just let me know and I'll set up a Zoom appointment. But good luck. And like I said, don't hesitate to contact me if you need help. All right, thank you very much.